All right, welcome to another version of breaking down the most commonly confusing and conceptually difficult topics in GIS. We'll speak in a general sense about spatial statistics and spatial autocorrelation, and where students generally, have issues of confusion or not completely understanding these topics. Again, it's me, Dr. Harmon. Um, I'm a teaching associate professor at Western University. I work in the geography department. My office is just um, off to my left in this picture in Brooks Hall. There's my email and the website for our department. Check us out if you have any questions or you want to know a little more about something. Spatial statistics and spatial autocorrelation. So really there's a couple of things. Number one is one of the reasons students struggle with this is basically you take statistics and you take geography, and when you combine them together, you've just got something that's now doubly tough. Students already find statistics, harsh at times, and adding a spatial component to it makes it, infinitely levels more confusing at times. um, the other big misunderstanding that I'm going to talk about right now is randomness. Um, Students will, on occasion, get in their head through one means or the other that randomness means that things are like evenly spaced out, which is actually not random. That is dispersed. Um, when statistically random points, in fact, often they form clusters. So if if you find that confusing, the way I like to think about it is it's a mix of evenly spaced and clustered things. Sort of imagine like we have this thing called we'll call it a space cookie. All right. Um, and the cookie is just space, and it's filled up with just randomness. Okay. The cookie part is the even spaced part, and they're chips of scattered randomness across the cookie. Um, in no specific pattern, just wherever they land. So you think of like a cookie with the chips in it. The chips are where the the data is not evenly spaced apart. That's where the data is grouped into tiny little clusters or something like that. In other areas, its space is consistent. It's just cookie. But when you throw in the space chips onto the space cookie, you get little bitty clusters. I don't know if that makes sense or not, but hopefully that'll kind of get you to thinking about it. That when we talk about random, it doesn't mean that there is a pattern. It means there's not a pattern. And evenly dispersed is a pattern, so it can't be evenly dispersed. It's got to just be, and this is a horrible way to explain something as, how do you describe random? As well, it has to be random. So I'm not going to do that, but that's what I really wanted to say. Um, if we were to try to explain spatial statistics in plain language, it would go something like this. Spatial statistics are just basically regular statistics with some degree of geography built in. They just ask a slightly different question. They don't just focus on values, but they also focus on location, where the values are. So instead of treating each point or polygon as isolated, spatial statistics looks for patterns. Are things clustered? Are they spread out? Is something completely random? Do areas influence each other, or are they independent? This extra where component lets us detect things like hotspots, find spatial outliers. It allows us to build better models that account for location rather than just ignoring it. And that is really the strength of spatial autocorrelation, is that it allows us to do these things. It asks the simple but powerful question: are nearby things more similar than things that are further apart? Spatial autocorrelation, it does feel kind of counterintuitive sometimes to students. They struggle with the idea that nearby values aren't independent because all the stats you've done on your life up to the point the first time you do spatial statistics, everything's got to be, independent. And now we're talking about we're going to do stats where we're counting on things being um, dependent on one another. So that creates sort of a mental hurdle that you got to get over. And once you do, you'll come to realize that spatial autocorrelation, it's actually a good thing. We use it, we rely on it, in fact. Um, Now, the basic concepts of spatial statistics, I'm going to explain it sort of in the context of Moran's eye. So Moran's eye is a lot like a correlation coefficient. The higher the number, the more positively correlated. The lower the number into the negatives, the more negatively correlated. And so if we're at one or more, we're perfect clusters. And if we're at a negative one, then we're at a perfect checkerboard pattern. Another meaning that everything is evenly dispersed from one another. And if we're at a zero, it just means it's random. What does that mean? It means there's some clusters and there's some checkerboarding going on. And that's essentially what we're doing. Is looking at the location of all these values with something like Moran's eye, and we're saying, okay, is there something going on with these points? Are they lumped together? Are they spread out? What have you? Excuse me. I apologize for the coughing. That's what spatial statistics really does. Is it allows us to look at that aspect of this when we're looking at differences in values. So positive spatial autocorrelation means similar values clustered together, like high crime neighborhoods next to other high crime neighborhoods. Negative spatial autocorrelation is when nearby values are very different. So like we have high values right beside low values, right beside high values, right beside low values. That would be like a negative correlation. When there's no spatial autocorrelation, the pattern is random and the relationship really doesn't hold with location. Now, spatial autocorrelation itself sort of follows this idea that things that are close together tend to be alike. Now, it's important to remember we didn't say they're the same. No, we said they're alike. If your neighbor's houses are expensive, chances are yours is too. And if you have one field on your farm that has very poor soil, chances are the field right beside it is probably going to have really poor soil as well. Spatial statistics lets us measure how strong those relationships are instead of just eyeballing them and taking a guess or making something up. We can actually measure the strength of that correlation spatially. We do this with both global and local measures, and students can get lost trying to differentiate between the two. Like Moran's eye, for example. That test summarizes the whole data set, whereas local measures like ELISA, a local indicator of spatial autocorrelation, it detects individual hotspots or outliers. Now, global results, they can't show you what the pattern is. So they're really just best for things like describing the general trend, like I have a data set. Is it spatially autocorrelated? Yes or no. Looks at the data set as a whole and says yes or no. Where local results tend to guide decisions about where to do like focused interventions, where to put up speed traps, where to add extra policing, which school systems need extra funding, that kind of stuff. It helps you find hotspots of whatever you're measuring. Now, global measures, they can help confirm that you have spatial dependence and it exists, which is useful for a lot of modeling endeavors. But local measures, on the other hand, they reveal where the predictions may be more or less reliable. So you could determine that you have spatial autocorrelation, and then you create some sort of a spatial model to express this value across some larger area, and then you can look for the global or the local measures rather, and find those locations where that strength of that relationship is really strong. Those are the places where your model will probably perform a little better. So why is spatial autocorrelation foundational to GIS? Well, pretty much everything we do relies on this idea. You know, we draw a point here and we draw a point there and we put a line between them. It's how we map and interpolate across space and time. And it's dependent on near values being related to nearby data. It all comes back to Tobler's first law of geography, which is, in many ways, the single best explanation for why we can map things geospatially. It's that everything is related to everything else, but near things are more closely related to each other than things that are far apart. Here's some other hangups that get students once in a while. Spatial weight matrices is one of them. A spatial weight matrices defines which features are considered neighbors. That's all that really does. Is it helps you assign that neighborhood area. We can do that based on things like shared borders or contiguity, or maybe it's some sort of fixed distance, or it's the closest few features, like the k nearest neighbors, where you pick a number. It's the closest 10, 5, 2, 28, 113, whatever it is. This choice helps you control how some of your spatial statistics, particularly with the things that involve these matrices, are really calculated. Another thing that kind of grinds people's gears sometimes is the concept of significance testing. Spatial testing like Moran's eye or Geddes and Ord's GI star, they got to be tested to see if the pattern is more extreme than just random chance. So they do that with z-scores and p-values. They do the z-scores to figure out the p-values. And how unlikely your results would be if the point were just randomly distributed. That's sort of what works into it to figure it out. Low p-values less than 0.05 means that clustering or dispersion is statistically significant. And this is all done through some variations of permutation tests. It randomizes the data and builds all this reference till it creates this beautiful distribution made from the data, and then it says, okay, where does the real numbers fit on that manufactured distribution? And from that, you can get these other values. Some common pitfalls that you got to keep an eye out for. You got to be aware of issues that can mislead your interpretation. So, number one rule when you're doing any kind of spatial analysis or spatial statistics, if you're going to use that result to make a point, or if it is the penultimate step in your analysis, or if it is the actual ultimate thing you're trying to answer, that's great. If you do not understand fully what those results mean, don't do it. Okay? If you don't understand the results, there's no way you can interpret the results. So fundamentally, once you recognize that a certain test or something is the appropriate one for what you want to do, it behooves you to become sort of a moderate scale expert in that test. You need to really work up your skills on it, read about it, look at examples of it, see how other people describe it until you truly understand what it does. Another one is the modified error unit problem, MAUP. And this means results can change if you use different boundary units. Um, and you really have to watch for the effects of that and what it can mean to your analysis. I'll do a video on this topic specifically later. Edge effects can also distort results near the edge of your study area. So things like k-means or neighborhood statistics or anything that uses some sort of a moving window, you really have to be cautious of, because as you get to some of these cells or areas that are right along the borders, they don't have a full complement of neighbors in all directions. And that can really skew your results. And so there's always going to be some level of trepidation in terms of looking at what those values are along the edges of whether it's a polygon or a raster, either one. So hopefully this helped clear up some of these topics if it was something that you were stuck on, needed a little extra lecturing. And if, by the way, you find yourself interested in pursuing your education further, at West Virginia University, we offer a fully online, fully asynchronous, affordable MS degree that's nationally recognized. It's available to students everywhere, and we have virtual information sessions multiple times a year. You can go to this link here, this website, page. It'll take you to the one about the degree program, tell you all about it. There's a spot on there that you can register for one of the information sessions if you want to know more. So if you're thinking about advancing your geospatial knowledge, advancing your careers, picking up an additional degree, uh, we support that. We think it's awesome. We hope you choose us, but if not, we hope you choose someone. Um, we believe in the power of GIS at West Virginia University, and the more people that understand that, that appreciate that, that do that, then we'll all see the rewards, not just in the jobs and the prestige, but in the science and the work itself. All right, that's it. Um, Stick around here in a couple seconds. There'll be a thing you can click to subscribe if you want, and there'll be a recommendation for another video to follow up if you're just love listening to me cough on YouTube. So have a great day.